The arrangement of electrons in an atom determines how reactive the element will be. So when we're talking about reactive, or in this word reactive, we're talking about how chemically reactive. So will a metal such as sodium explode in water? Okay? Or will a metal such as gold, when it's added to water, just sit there and not do anything? So when we talk about why elements react, it is because of the arrangement of their electrons. And the electrons, as we spoke about previously, are found in a cloud. Okay, we made an example of the fan in the classroom and the electrons spinning. And we said that they can just easily be said to sit in these things called shells. But what did we add to that? We said they were something shells. Great, they were electron shells. Now, the number of shells, okay, depends on the number of electrons within an atom. So if we have lots of electrons, we're going to need lots of shells. Now, each shell can only hold so many electrons. All right? You could almost think of it like a bag can only hold so many things before you need another bag. And then you fill a second bag up, and then you need a third. Now, when we're talking about how many electrons can fit into each bag, some bags are smaller and some bags are larger. So our very first bag that we go out with is a very small bag. It can only fit 2 electrons. The second bag can fit 8 electrons. The third bag can fit another 8 electrons. And what we call this is the 2-8-8 rule. Now it only works for the first 20 elements. Okay? Only works for the first 20 elements. After that, it gets rather complicated. And then we switch to letters instead of numbers, and life is miserable. So we're going to keep it really simple this year, and we're just going to worry about the first 20, and you are going to worry about this 2-8-8 rule. So let's talk about what that means. It means that in the first shell, there are only 2 electrons. And what I'm going to do is, on this diagram below here, I'm going to highlight in green that first shell. Right? We're going to fill in some stuff into the green shell in a second, but I just want to make it really clear. So this shell, the inside shell, how many electrons are going to fit in there at maximum? 2. Now if I had, say, 3 electrons, 2 will fit in the inner shell, and then 1 is going to move into the second shell. And the second shell can only fit a maximum of 8 electrons. So this is my second shell here. The third and final shell can also fit 8 electrons. So let's imagine now I had a total of 13 electrons. 2 of the 13 would go in the inner shell. 8 of the 13 would go in the second shell. So how many would be left in the most outside shell? 3. Giving us a total of 13 electrons. Now what you'll notice about these electrons is if we only have 2 electrons, as we've done in our first shell, it's what we call low energy. There isn't much energy held there. When we move on to the second shell, it is slightly higher energy. And by the time we get to our third shell, it is packed full of even more energy. So what we're going to do together now is we're going to have a look at oxygen. Okay? So let's break oxygen down together. This is oxygen as it appears on the periodic table. So what does this number up the top here represent? What is this number? The atomic number. Very good. So I'm going to get you to label that one in your book as well. If we can remember which number represents the atomic number, it can make our life very easy later on down the track. So the atomic number, what does it represent? Number of protons, neutrons, electrons? Protons. So, in this instance, we are going to have 8 protons. And in an atom, we have the same number of electrons as we do protons, which means how many electrons do we have? 8. Now, for this next one, we need to use this number down the bottom. What does this number down the bottom represent? The mass. So this is the atomic mass. And as you may remember from a few lessons ago, the number of neutrons is equal to the mass take away the atomic number. So in this case, if we look at the mass, 16 minus 8 gives us how many neutrons? 8. So now that we've done a little bit of recap and we've looked at an atomic number and atomic mass again, let's talk about electrons. Now, I like to draw my electrons as a little e with a minus at the top. Why do I represent them with a minus at the top? Great, because it has a negative charge. So when I look at oxygen, it has how many electrons all up? How many is it going to have? 8. Okay, it's going to have the same as its number of protons. So if we look at our first shell, how many electrons fit in that first shell? 2. So I'm going to draw 1 electron at the top, and I'm going to draw 1 down the bottom. They like a little bit of space, these ones, in the inner shell. In the next shell, how many electrons am I going to have? 6. Why is it 6 and not 8? Because it's 8 in total. And I've already put 2 into my inner shell, which leaves me with 6 left over. Now, because the second shell and the third shell are a little bit larger, the electrons get a little bit lonely. And they like to hang out with a friend. So what we normally do is we draw them as a pair. So in this second shell, we have 6 electrons, and I'm going to draw them as 3 pairs. Because that shell is a little bit larger, and again, they like to hang out with a friend. Yes, please. Yeah, so please fill this drawing in. So when we talk about the electron arrangement now for oxygen, well, we can say how many electrons are there all together, and we can count them. So we can see on the inner shell, 1, 2, and then in the outer shell, 3, 4, 5, 6, 7, 8. And that lines up with our next question, which is the number of electrons in each shell. So in the first shell, we can see that there are 2 electrons. In the second shell, we can see that there are 6 electrons. Are we ever going to get to the third shell? Do we need a third bag for all these electrons? No, not for oxygen, so no. Beg your pardon? No, because we just don't need the extra bag, okay? So in this case, we keep it to the first and the second shell. We really don't want to carry around an extra bag, an extra shell, if we don't have to. Okay? So when we're talking here, write the electron configuration now. We represent it. Remember our rule was the 2-8-8 rule. We write it in the same way. So how many electrons do we have in total? We only have 8, and they're spread as 2, 6. You don't need to, no. So you don't need to worry about a 0 for the third shell. You just need to say exactly how many electrons there are. So 2 in the inner shell, 6 in the second shell. So draw a diagram of an oxygen atom in the space below. So this is going to be ever so slightly different to this one up the top. How is it going to differ? Yeah. Yeah, so what we're going to do now is we're going to represent this one quite clearly. So as we said, how many protons do we have in an oxygen nucleus? 8. So we're going to draw 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to do a little key over on the right to say that these ones are my protons. Next up, in a different colour, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. Now, my diagram here isn't amazing. You know I'm not the best at drawing, but really the protons and the neutrons should be roughly the same size, okay? So these are my neutrons here. And now the only thing that we're going to do differently to how we've been doing this previously is we're going to draw the electron shells. And so in this case, in the first shell, we have those 2 electrons. And because it's a small shell, they've got a little bit of space in between them. They're not too far apart. But in the second shell, remember they'll get lonely if they're all by themselves, so they like to hang out with a friend. And so we draw them as a pair. And as we've just established in the second shell, there are going to be 6 electrons. And then I just draw a line showing that these together all form a big shell like that. So can everyone really clearly see now? On the inside we have this first shell. Is the first shell low or high energy? Low energy. And then as we get into the second shell, it's slightly more energy. Okay? Slightly more energy. Are there any questions around the room before we move on to practicing drawing some electron configurations? Yeah. Mm-hmm. It is 6 electrons in the second shell because oxygen has 8 all up. Because we have 8 protons in the middle here, and that means we're going to want 8 electrons so that everything is nice and balanced. Okay? Now, the reason we only have 6 in the second shell is because we've already dropped 2 into the inner shell. So 1, 2, 3, 4, 5, 6, 7, and 8. Yeah? Hey. How do we know that there's 8 neutrons? Because our atomic mass was 16 for oxygen, and the atomic mass is equal to the number of protons plus the number of neutrons. So in this case, if we know that the mass is 16, we know that we have 8 protons from the atomic number. 8 plus what gives us 16? 8. And so that's how we can determine the number of neutrons.
What's the reason for the equation? Is it because of the charge? Is it because weight, mass?
It's because of the mass.
Because neutrons and...
Neutrons and protons both have a weight of 1. Electrons have a weight of 0. Yep.
What happens if it's over the first or the other ones?
Then it changes, and that's when we get into the letters S, P, D, and F. And it completely changes. No, you don't. So we're going to keep it really simple. Were there any other questions? All right, so what we're going to do now, you're going to have a go at drawing all of these ones now. And we're going to do the first 3 together. Now the last 2, potassium and calcium, are really tricky because they've got a 4th shell. And I haven't taught you explicitly what to do in a 4th shell, but I trust that you'll be able to do it quite well. So let's do the first 3 together. Hydrogen, it is element number 1. It is going to have 1 electron. Now, I've told you that we draw our electrons as an E with a little minus. In this practice, I'm going to be very happy for you to represent them as either dots or crosses. And what I mean by that is, for this first one, I'm just going to draw 1 dot like this. Happy? No, you don't. Not this time. No, we don't need to worry about the nucleus in this case. That is okay. As I scroll over to helium, now in that inner shell, do the electrons want to be together or do they want to be apart? Apart. Because it's such a small shell. So what I'll do in this case is I'll represent them as little crosses. So 1 and 2. I then go to lithium, my next element, number 3. And because lithium is number 3 on the periodic table, it is going to have 3 protons and 3 electrons. So this means lithium goes 1 and 2. Do we have any more room in this shell? No, so where does the next electron go? To the next shell. It's all by itself. It's really sad. So I'm going to trust you now. Have a go at the other 17. I'm going to wander around and I'll help you out. I want you to use your periodic table for this next page. Okay? You get to use it. You get to use it in a test. You need to practice using it. So please, don't go without your periodic table. Use it. Let's look at lithium together. So we have 3 boxes here. We have atomic number and we have number of electrons before we get to electron configuration. Question? Oh, apologies. Let me send that one back up there. There we are. So when we're looking, lithium, okay? If you use your periodic table, can you please put your finger on lithium? You will see that lithium is atomic number 3. In an atom, we know that the atomic number is the same as the number of electrons. So we're going to say 3. How are these 3 spread across their shells though? How many electrons can we have in the first shell? 2. And how many is that going to leave for us in the second shell? 1. Perfect. Let's look at one more example together. I'm going to scroll all the way down to silicon. Can you please find silicon and put your finger on silicon? You will see that silicon is number 14. This means that it is going to have 14 electrons, and they will be spread across a few shells. In the first shell, we will use 2 electrons. In the second shell, will we have 8 or will we have less than 8? We will have 8. And then in the final shell, we will have 4. Excellent. So what I'm going to get you to do now, can you please have a go at completing that table in full for me? We have a look at this final table here. Before we get into it, we're just going to look at this final thing up here, which it asks us to look at the outer or final shell. And this is something that's really important, so we're all going to highlight it in our books together. Electrons located in the outer or the last shell of an atom are called valence electrons. And I'm actually going to underline that term, valence electrons. It's very, very important. You have your terminology page at the front of your booklet. I would encourage you to copy that in shortly. But for now, what we're going to do is we're going to look at the valence electrons in this table. The valence electrons are always going to be those in the very outer layer. I've highlighted mine here. Your table will be complete. You'll have plenty more. What we're then going to do is we're going to fill in this table together. So if we have a look, we can see that element number 5, boron, is represented using atomic notation. Its weight is 11. So when we look at the atomic number, this is the same as the number of protons, which is 5. We look at the mass number, we can see that the mass is up the top left, it is 11. The number of protons is the same as the atomic number, which is 5. The number of electrons is the same as the number of protons. The number of neutrons is equal to the mass, take away the atomic number, which is 6. And the electron configuration, we know that we have a total of 5 electrons, 2 fill up the inner shell, and that leaves how many electrons for the second shell? 3. So when we look at this electron configuration of 2, 3, how many are going to be those valence electrons? How many are going to be located in the outer shell? 3. Fantastic. Your job now? Finish off everything. Let's go.